Anyway, I like to congratulate Mahbuba Akhtari, and I am very much delighted to see her here because we always see some bad news regarding his university. But now we can see that there is the other side is also true. Thank you, and
We can go for the next. No, sir.
We can declare
no,
absent.
so total we had 5 papers, out of which 3 are present and 2 are not present.
Who are not present, absent.
Yeah.
But actually,
Sir, I see the last one, maybe
Present?
present now, the last one.
Yes, I'm present.
The last one is, yes. The last
present?
paper. Yes, sir.
55, the author is present here.
Yeah.
So you will present the last one.
Mahbuba Akhtari. Okay, please come up. Start your presentation.
Okay. Thank you so much.
I think you can do it.
Paper ID 55, is it?
Yes. Yes.
Okay.
Thank you so much for inviting me to present my research work on materials science field. And I'm really honored to be in front of you, dear scientific community, researchers, and students. I express my sincere thanks to IEEE Computer Society Bangladesh Chapter Summer Symposium 2021. And the title of my presentation is Exploration of Whole Conductivity. Sorry. May I share my screen?
Please share your slide.
Okay.
Yes.
Can you see this?
Yes.
Okay.
Please go to the slideshow mode.
Yes. The title of my presentation is Exploration of Whole Conductivity in Multifunctional Zinc Antimony Silver Doped Oxide. And as I am an undergraduate student, so I would like to mention you that our university doesn't offer any research program for undergraduate level, and I'm highly interested to learn about research work, and so I have I have started in the beginning very early, and I would like to share my some research experience which I've experienced before. And in 20 can you see me?
Yes, continue.
Okay. Okay, I'm from Begum Rokeya University, Rangpur, and I attended third International Conference on Physics for Sustainable Development and Technology in 2019 and awarded for Best Poster Presentation on Perovskite Material. And here is another one attempt to International Conference on Physics 2020 organized by Bangladesh Physical Society, Dhaka. And this is my third international conference, and I'm really honored to be invited here to deliver my speech. The outline of my presentation is the outline of my presentation is introduction, motivation, theoretical approach based on cascade density functional theory and optimization, and results and discussion. Let's see why post-transitional metal oxide is important in this field. We know the transitional metal oxides are mostly abundant in Earth, and it has many fascinating properties based on due to their partially filled d orbital, wide band gap, chemical and mechanical stability, thermal stability at room temperatures, and excellent transparency, absorption, and large binding energy. Here we can see the figure on the right side, the D10 configuration, electronic configuration for a post-transitional metal oxide as zinc oxide, and here we can see the electronic configuration and subcell of these electronic states. As I have chosen that zinc oxide as a post-transitional metal oxide for my research work. So I would like to mention you why I choose that. Why zinc oxide? The wedge zinc oxide is a hexagonal crystal structure of a space group P63MC. And here you can see in figure on the left side, the powder zinc oxide sample is present here, and on the right side, some of the optoelectronic device applications are mentioned as metal insulator, semiconductor, heterojunction, PN homojunction, electrically pumped random lasers, multifunctional electronic, piezoelectronic transducer, surface acoustic wave devices, and gas sensor applications for future application of zinc oxide. Now, I would like to mention and review some motivation behind my work. Point defect and vacancies in zinc oxide can be a blessing for us if we can put a right atom in a right place. And here, the doping is powerful tool to tailor the electrical, chemical, magnetic, and optical properties of zinc oxide. Group 1 element, Group 1A and Group 1B and 5A elements are worthy for shallow and deep level acceptor for doping impurity for doping or impurity element. The interstitial site incorporated some difficult issues for the fabrication for our purpose. One attempt was using 1B element instead of 1A to overcome the issues arises from oxygen vacancies and zinc interstitials. Recent research on successfully fabricated silver nitrogen zinc oxide nanotube gave the evidence of p-type conductivity with enhanced optical properties at visible region. But the problem was that the limited number of silver for substitutional zinc site. Here you can see that I mentioned that p-type conductivity, and p-type conductivity is rarely found in research sector, and we have great concern about getting and designing p-type conductive element. And here we try to overcome the problem of rare and unstable p-type conductivity by implementation of antimony with silver dopant for zinc oxide to produce acceptor level which pushed Fermi level to the valence band. Let's see the theoretical approach. My work is based on computer simulation and designing and investigating some other properties of this new material. And here I have used Materials Studio software to simulate and design a new material based on zinc oxide. Here you can see the figure on the left side, A and B, the undoped and doped zinc oxide structure, supercell 222, and I simulated the supercell with cutoff energy 400 electron volt, and I set the K point as 442. I carried out this calculation using Cambridge serial total energy package, actually gas step code, and the first principal calculation was carried out using pseudo-potential method, ultrasoft pseudo-potential method, which is actually another application of density functional theory, DFT. And I optimized the structure geometry optimization to get a reliable computational result. And after that, I characterize some structural properties, electronic properties, and optical properties using GZA, actually generalized gradient approximation I've used to clarify and to get more reliable result for exchange correlation. Here you can see the structural properties of zinc oxide, single doped zinc oxide and dual doped zinc oxide. The lattice parameter in this table, you can see the lattice parameters and band gap for undoped, silver doped and silver antimony doped zinc oxide. Can you hear me?
Yes,
Yes,
continue.
yes.
Continue.
Okay.
Please continue.
Okay. Here my network is unstable, so I have to be concerned about my connection. Okay, thank you. Results and discussion, and I have shown that structural properties in table 1, lattice parameters and band gap for undoped zinc oxide, silver doped zinc oxide, and silver antimony doped zinc oxide. Here I have used the concentration or percentage of silver and antimony doping for this dopant element as 6.25%. And I substitute this on zinc site, and here oxygen site is stable. And here we can see a remarkable change along C-axis than A-axis, and the growth of C-axis arrangement orientation is performed using this computational method, and we have found some extraordinary facilities and some band gap engineering applications for these materials. And we can see the hexagonal close-packed ratio C over A has not significantly changed over this computation method. And so the evidence of existing the hexagonal phase for both the cases are ensured by this computation. And volume is increased. You can see for doped and undoped element. The undoped element was less volume, and after doping and co-doping, the volume has been increased many times. Increased significantly. And this increment was due to the large dopant size and ionic radii of this silver and antimony. And here you can see some band gap values calculated by our computational method based on cascade code. And there the value of band gap has been first lowered by silver doping, and after then if we implemented antimony with silver on zinc side, then we can find a larger band gap value. Now see the electronic property of zinc oxide. The figure on the left side represents the energy band diagram, which shows that direct band gap with band gap value 0.763 electron volt, and the difference between lower potential of the conduction band here, pointed here, and the upper potential of the valence band is actually energy band gap, and its value is 0.763 electron volt. And high curvature of this diagram indicates low effective mass and high mobility of electrons of intrinsically intact zinc oxide. And the figure on the right side, here we can see the partial dose and total dose representation with energy and
2 minutes remaining.
Okay. We can see the valence band contribution was arised from the 2p oxygen 2p and zinc 3d orbital, and conduction band peaks are arised from the overlapping of the oxygen 2p and zinc 3p orbitals. And electronic property of silver doped zinc oxide. Here we can see again on the left side of the band structure diagram, and it has the lowered band gap value 0.219 electron volt with direct band gap. Since it has the same momentum value G, and transition is direct, so it is a direct band gap semiconductor, and a new acceptor level is generated above the Fermi levels and near the valence band, which is the strong evidence of the existence of p-type conductivity. And high effective mass is shown by the less curvature of this energy band diagram, and it has less mobility. And on the figure of right side, we can see the partial dose and total dose representation, and the valence band contribution was arised from the contribution or overlapping of silver 4d orbital, oxygen 2p, and zinc 3d orbital. And conduction band peaks arise from silver 4p, oxygen 2p, and zinc 3p orbital. Electronic property of silver, zinc, antimony silver doped zinc oxide. Here we can also see a band structure and direct band gap with energy band with energy 0.666 electron volt, and here impurity states also generated near the valence band, and which is also a strong evidence of p-type conductivity. The flattened curvature of the energy versus K diagram shows the high mobility and less effective mass of holes, and pools, which is actually resulted from repulsive potential increased to increase the band gap. And valence band peak were arised from the overlapping of zinc 3D, oxygen 2p, silver 4D, and antimony 5p orbitals. And the conduction band peaks were arised from the contribution of zinc 3p, oxygen 2p, silver 4p, and antimony 5p states. Now see the optical properties. The optical responses of semiconductor material is has great concern in research community and scientific community for their extraordinary and mesmerizing properties in research field and application sectors. The dielectric constant actually represents optical response of this material, and we can calculate many other optical properties by explicitly or implicitly with this dielectric function. Here we can see the figure on the left side. Static dielectric constant at zero frequency indicates the incremented value, and imaginary part shows optical transition between occupied and unoccupied states, and negative values of real part indicates the complete reflection of photon at corresponding energy. A new peak of dielectric constant arranged near 2 electron volt for undoped, arranged near 2 for undoped and co-doped structure, but it disappeared for silver doping due to the lacks of sufficient empty state of silver atom for electronic transition. And the figure on the right side here, we can see the conductivity representation of this material, and at higher absorption spectra, more electronic transition produces more holes, and hence the conductivity become high with energy. Optical properties can also be extended.
Your time is up.
Can I get one? This is the last slide actually.
Okay, please quickly close quickly, very quickly you can close.
Okay. The optical absorption spectra is actually increasing, and it's that optical absorption represent the electronic transition between the unfilled and filled and unfilled state. And here we can see a peak near 7.13 electron volt is due to the impurity states generated by silver and antimony on zinc side for co-doped structure represented by red color curve. And here the evidence of ultraviolet absorption, which is a very, very effective sign, very effective sign for the optoelectronic device application. And here on the right side, we can see the loss function, and we can see with frequency increment, the loss function value is increasing for a certain value and sharply decreased. And for single dot and co-dot structure, we can minimize this frequency for this maximum loss function. The conclusion of my presentation or research finding is that the elongation of C-axis orientation due to variation of ionic radius size of dopant and host atoms, and the C over A ratio confirms the hexagonal structure, that is the unchanged phase of this material, and the band gap has tuned significantly for our future applications, and N-type to P-type transition occur due to silver and antimony doping. The curvature analysis of energy versus K diagram confirms the increased hole mobility, which is very interesting topic in our research field. The material can be efficiently used in P-type based electronic and optoelectronic devices homojunction applications with significantly enhanced output power. And thank you. all audience and researchers for introducing me and giving me an opportunity to say something about my topics and share my views. And though there is a lot of limitations in our laboratory, and I'm an undergraduate student, I couldn't get fund for experimental exploration of this research work. And so this was actually theoretical one. And thank you so much.
So you are the only author of this paper?
No.
Or do you have any other?
Yes, I have to mention that I'm working under the supervision of two supervisors in my department, and they support me to go to computer lab and use their facilities, and that's all. And some of other references. These are the references and the introduction of my research work. Thank you so much for your valuable time, and please, if you have any suggestion or any question, please you can ask me.
So this conference is not a relevant conference of your research work.
Yes, I know.
So I suggest you. To submit your paper in some of your relevant conferences.
Yes, but I thought that since I have computed, since it is a theoretical work and it was based on CASTIP code, so.
You just use some simulation software.
Yes,
and
yes,
also
yes.
Investigated this one.
Yes.
But here is algorithms and computation means that you have to develop some algorithms or something.
Oh, I see.
Okay, thank you. I think that is the part of the organizers. They have selected this paper for presentation. They
Yes.
took care of this.
Yeah.
Anyway, I like to congratulate Mahbuba Akhtari, and I am very much delighted to see her here because we always see some bad news regarding his university. But now we can see that there is the other side is also true. Thank you. And now I have some query that did you think about the fabrication challenges of this type of semiconductor? Is there any facility in your laboratory?
Yes, of course, because I think that the most important facilities is to getting cordial supervisor or cordial teammates for conducting this work. And after that,
now, as you have mentioned that you are a UG student, so I like to know whether there is any PG student also working on the same field in your university or in your department.
No. I'm the first one. I'm the first one in my university.
Okay, thank you. I think you can extend your work in future in different directions. I like to know one thing, that did you consider that the visibility or transparency of optical properties, it is a function of the wavelength also?
Sorry, I didn't.
Can you throw some light? The optical properties.
Yes.
Because you are thinking that this zinc oxide semiconductors can be used for photovoltaics also, is it?
Yes.
You have shown some. So if it is so, it is wavelength dependent. Wavelength of the light. Have you ever tried this one?
No, sir.
Do you know that? Do you know that there are different wavelengths available in the sun rays?
Yes.
It extends from 40 nanometer to 400 nanometer to 700 nanometer visible light.
Yes.
And the optical properties are very much dependent on wavelength.
Yes, sir.
Okay, thank you. Sir, Dr. Sajiraman, sir,
Okay.
already Azan has shouted.
Yes.
So,
so I think the other author of other paper is absent still now.
Yes.
Yeah,
Yes.
still no. I have checked. He is present. He is not present. So we can close this session.
Yes.
So
Okay,
we like
thank
to.
you all.
Yes, Dr. Shahina Sultana, please continue. Dr. Shahina, please continue. We like to hear.
Thank you for your presentation,
You're welcome.
and thank you all for this to attend for this session.
You are most welcome, ma'am, and all. And thank you so much. And wish to see you again.
So I'd like to thank the organizers.
Sir,
also
1
for-
minute, sir. Go first, sir. 1 minute.
Yes.
We would like to hand over our token of appreciation. Okay. Now we would like to hand over our token of appreciation to our honorable session chairs. At first, it goes to our Professor Dr. Muhammad Abdul Ghaffar Khan. Thank you very much for your valuable time in this holiday.
Thank you very much.
Then the appreciation goes to Dr. Shahina Sultana. She's actually working for us for 2 years. Last year, she also helped a lot. And this year, she willingly has been assigned to chair the sessions. Thank you, Shahina madam.
Thank you.
And finally, it goes to Dr. Muhammad Saidur Rahman sir. He's our technical chair. And this is the very toughest session papers he has to evaluate. And thank you, everybody, all the reviewers, all the session chairs and participants for joining with us. Thank you, everybody.
Thank you,
Assalamu alaikum.
everybody. Assalamu alaikum.
Later, we
Thank
will
you, everyone.
email you the certificates we will be sending our team. Thank you.
Thank you, everyone. We would like to end today's session here.
You're most welcome.
So our next session will be after Juma prayer. What time? From 3 p.m.